Hello everybody, good morning, good evening, good afternoon. My name is Wojciech Węgrzyński. I'm with the Building Research Institute of Poland, ITB, and today I will talk about multiparametric CFD analysis that we have used to better understand key variables determining performance of smoke control systems in car parks. Let's jump straight into it. Car parks, they're very interesting to me, both scientifically and from my practical engineering point of view. Car parks are buildings that are very similar in principles, systems used in them, and their operational characteristics. Yet the tiny details in architecture, such as inlet, outlet location, entry points, etc., create a very diverse array of buildings that we have to deal with, and in the end each car park is very unique. Car parks are on the forefront of innovation that has some consequences to the fire safety challenges we face. There's a lot of new technology such as stacking systems or automated stacking systems in car parks that are commonly used today to save space. And we of course see a lot of innovation in vehicle technology that brings its own challenges to the fire safety of car parks. Conditions in the car parks are usually quite good for a fire to develop because you have a lot of fuel. Cars are filled with plastic, so they create quite a significant fire load. And the ventilation conditions are usually quite favorable because of the operation of the car park requires that. So that's quite a nice place for a fire to develop. And in some cases you might have quite a significant human presence in the car park when it's built next to a shopping mall or next to a sports venue. The risks related to car park fires are not something that we can forget. The consequences of car park fires may be significant, and in last years we have seen some examples of that. For example, Liverpool Eco Fire, where a car park next to a sports arena was destroyed, or in the same year Moscow shopping mall fire, where the shopping mall above the car park was completely destroyed by the outcomes of this fire. Similar thing happened in Cork, where the car park was so damaged after a fire that the shopping mall above it had to be closed. And finally, in this year, the Sola Airport fire in Norway, where a steel structure of the car park actually collapsed. This illustrates the fact that consequences of a big fire in a car park may be very severe, especially if the car park is part of a larger building complex or is connected with other buildings, because in that case the risk related to the fire in the car park extends to the buildings above and in the nearby. Obviously we want to control that. We don't want such consequences of fires in our built environment. This is why we protect the buildings with passive active systems, and one of such systems is smoke control system, also known as smoke and heat exhaust ventilation system. This type of a system does not prevent or contain fire, but the idea is that introducing flows of air, we can significantly change the flow field and exposure of the building and users to the smoke and heat. On the bottom of the slide you can see a simulation of a 20 megawatt very large fire in a car park without and with a smoke control system. And to the right you can see the difference between these two simulations, and what you can see on this plot is that the temperature difference between a case without ventilation and with ventilation at a large part of the car park is larger than 200 degrees Celsius. That's astounding difference, especially if you think that the radiative heat flux is in the fourth power of temperature. So the exposure conditions in those two simulations are drastically different, and this is what we want to achieve with the smoke control. We want to change the flow field and reduce the exposure of the users and firefighters to heat and smoke. smoke control systems are obligatory in multiple law systems, such as in Poland. In car parks in Poland, larger than 1.5 thousand square meters, you need to use them. And when we design car park smoke control, we usually care about either life safety, firefighter operations, or both at the same time. There are two prevalent technologies on the market that are commonly used in car parks. One is a duct system, in which you place arrays of ducts in your car park underneath the ceiling with exhaust points on them, and you intend to remove the smoke from a smoke layer that gathers underneath your ceiling. So there's a layer of smoke underneath the ceiling which you exhaust, and beyond underneath it there's a layer of clean air in which you can evacuate people or perform firefighting operations in. And the other system is jet fan system, in which you want to push the air through the fire so that the smoke, high temperature flow is between the fire and your exhaust point, while from the supply side you have fairly clean air that the firefighters can enter the car park with. And in this case, the smoke may fill the whole height of the car park. However, you want it to be between your source of fire and the exhaust point. What's important to me is that CFD is absolutely critical in the design of the car park smoke control systems. It seems very difficult, if not impossible, to design a optimal smoke control system in a car park, because they may have similar design scenarios, similar characteristics, even similar architecture, but because of the minuscule details of architecture, the outcomes of fires in car parks are very diverse. And yeah, as CFD is such an efficient tool to design car parks, we have also used that to identify the variables, the things that really matter when you design the smoke control system, and things that matter, the consequences of a fire. In the current project, I think this is our third multiparametric project on safety of car parks, the largest one definitely. We have used FDS to study outcomes in a wide range of fires in a car park with different heights, equipped with different systems. And this is the first project with this scale in ITB, so we also took the chance to develop some internal tools and frameworks to work with such a complex simulation project. The main model characteristics, we have used 15 centimeter mesh, which yielded approximately 2.5 million elements per simulation model. We have performed 480 simulations for the car parks, which took in total something like 1.5 months of continuous work of our HPC cluster. That's 78,000 hours, but that's only the simulations that were post-processed. Probably we've used more than 100,000 also on the when learning how to do that. Because of the scale of the project, if I wanted to investigate the results, like open the smoke view, take a look at the results, plot some images, let's say it takes me 3 minutes per simulation, that would be 24 hours of continuous work to go through all of the results in here. So it's absolutely unbearable. Thus we had to implement not only scripts for generation of the cases, but also for data acquisition and post-processing. And yeah, it was a challenge, but it was definitely worth it. For the variables investigated in the project, we've identified architectural, fire-related, and smoke control-related variables of interest to us. In terms of architecture, we have varied the height of the car park. That was the primary thing that we wanted to investigate. How the performance and safety of the systems and safety of the car park changed with the height. The area was fixed. It was 2.4 thousand square meters of the area where the smoke control systems were placed. The shape of the car park was rectangular, and the car park did not have any vehicles in it. Actually, we have a paper from a previous project where we investigated the differences between empty and full car parks if you're interested in that, maybe that one can help you. Related to fire, we did not use any probabilistic or deterministic fire development models. We resorted to design fires to keep it simple, to not introduce too much complexity. We have used standardized fires, TNO, which is a fire used in Dutch standard NEN about car parks. But we also used T-squared fires and some rapid fires for comparison. The other parameters related to emissions were rather generic, so not much to comment on that. In terms of the fire, if you take a look at the design fires you find in standards, these curves represent curves of a fire that was measured an experiment, and they are definitely useful for engineering analysis. However, for the research, we found that we're not really interested in the whole cause of this design fire. We are rather interested in parts of it, namely parts related to life safety assessment, the early stage of the fire, to see how the systems and height of the car park affect the evacuation phase. And we are interested in the conditions that the firefighters will encounter when they enter the car park. And for that, instead of using this growing and decaying curve, we decided to use steady-state fires to make it more simple. Because of the new challenges we face today with new types of vehicles in our car parks, we have found that we really want to see how different types of fires will develop in a car park. And for this reason, we have defined some design fires that, in our opinion, could be a resemblance of an electrical vehicle fire. At this point, we do not have a credible design fire for electric vehicles, and it will take some time to develop one. But one thing that we noticed is that electric vehicle fires, or battery fires in general, have this quite rapid growth. We don't know what the final heat release rate of these fires is, but we can guess that the growth is very quick. And for that, we have determined 6 different heat release rates that are very quickly developing in the car park, to see how a quickly developing fire will differ from design fires that we use in our design practice. In terms of smoke control, we have used duct system, we had used jet fan systems, we had one car park that was open, we had one car park without any systems. We varied the capacity of the systems. As the only variable, we did not play with devices. There is always some fine-tuning that you can do to improve the system characteristics, but in this case we kept them rather generic, and we only played with the major factor, which is the capacity. The workflow was quite interesting. As I mentioned before, we expected 480 cases, so that's a lot. To do that, we have used snippets of FDS code, parts of a code that describe the geometry, parts of a code that describe fire, describe sensors, and we used Python scripts to merge these snippets into cases. So basically providing snippets with parts of the code, we have generated all possible outcome cases from these combinations. And along the cases, we were generating some scripts to automate the computational process on our HPC cluster. And the same happened for the post-processing. We have developed scripts that take all the data from the HPC cluster, process it into individual data frames that describe particular variable at particular place. And from these data frames, we generate plots, we generate statistics as global statistics in the car park, min, maximum values. And in future, we also want to go deeper with an automated result analysis that I will hopefully be able to talk a bit more at the end of the presentation. So if we take a look at the results and just plot everything we got, it's not possible to draw conclusions from this body of results, because there's just too many. In fact, I think we literally received every potential outcome of a CFD simulation in the car park, from clean to completely filled with smoke. So that really proves that there's a huge variety in car park smoke control systems and car parks in general. To be able to draw conclusions, we have to focus on particular variables and narrow them down to be able to discuss and understand what's happening. And there's a lot of work in front of us to go through these results. It will be a book. It will not even be a journal paper. Well, hopefully there will be papers, but I think the amount of results we have obtained is such huge that we need to prepare a series large report that will meticulously touch each of them. Here I would like to share some most interesting ones with you. As mentioned, we've observed huge variability in the results. From car parks completely filled in smoke, and you are looking here at the visibility in smoke parameter, where red means no visibility and green is 30 meters. We had observed cases in which the whole car park was filled with smoke. We'd observed cases in which most of the car park under the same fire was clean. So the system was very efficient, and this shows you how varied the results of CFD analysis for car park smoke control can be. All of these are the same fire, the same car park, but different systems, and the difference is quite tremendous. Also, because these are results of fairly small fire, just 1.4 megawatt, if you try to investigate larger fires like 8 megawatts, you suddenly lose all the visibility, so you barely can do any comparison in visibility plots, but still the temperature plots and flow velocity plots show differences that allow us to draw conclusions on the performance of systems. Because the phenomena we do is transient, and we would like to investigate these things in a function of time, and it's very difficult to present results in two-dimensional plots that include time. We have used a lot of these space-time plots, and I wanted to explain how they work. If you put a line through your model and generate results along that line in a function of time, just stack the results as the time moves, you obtain this image in which in x-axis you have some space coordinate, in our case y coordinate, the width of the car park, and in y-axis you have the time. So this shows you the evolution of particular parameter along a particular line in a car park in the function of time, and this makes analyzing the outcomes of a simulation in time fairly easy. So conclusions. If the first one, the really profound one, is that for low ceiling height car parks like 2.4 meter, we have observed no favorable outcomes in the required safe evacuation time, no matter what system or scenario of operation we have used. No matter what we have done, no matter what we have put into the car park, we have never received satisfactory results of this simulation, even for very small 1.4 megawatt fires. It just seems that 2.4 meter ceiling height is insufficient to provide adequate life safety in an event of a fire in a car park. The smoke quickly fills the area. The smoke layer that forms underneath the ceiling is well below the level of head of a human, so it reaches 1.5 meter, so it's fairly low, and the evacuation conditions in such a car park quickly breach the tenability criteria. If you increase the height, though, you quickly observe much better performance of a system. And here, this is the lowest capacity system that we have tested, 17 cubic meters per second duct system. And you can see that for 2.7 meter, the performance is much better. And for 3 meters, this is something very, very nice. And this system actually provides tenable evacuation conditions in the car park during the required safe evacuation time, and even beyond if the fire does not grow further. If the car park is higher, the results are even better. Here we did analyze the percentage of cells in the car park at the height of 1.8 meter, at which the visibility was less than 10 meters. And for 2.4 meter, you can see that, for example, for 2.4 meter, even for 17, 34, 50 cubic meter per second systems, in all of them, despite the increase in efficiency, we have had most of the car park, more than 90% of the car park filled with smoke. You can also see that the difference between height, let's say from 2.7 meters to 3.3 meter, this 60 centimeter difference in height gives better effect than increasing the capacity of a system from 17 to 50 3 times. So it really shows you how important height is in the car park. And if we consider larger fires, the effects are very similar. It's just the more of the car park is filled with smoke, but still, the higher the car park, the better the conditions we can reach in it. And the higher the car park, the more efficient the exhaust systems are. That's connected with the fact that the smoke layer is higher, so less of it reaches the point where we have humans in. If we take a look at the jet fan systems, as mentioned before, they have different principle of operation. So we would expect them that at some point of the simulation there will be smoke in the car park. It's just it will be contained between the source of the fire and the exhaust. And one interesting fact we found here is that with the higher ceiling we had better results with jet fan systems. We expected different, that lower ceiling will increase the velocity of airflow in the car park, and the lower ceiling will provide better conditions than the higher ones for a constant exhaust volume. But it seems that the lower temperature that you have in higher car parks is more important. We'll look into that more in details, but so far it seems the same effects are present in jet fan systems, that car height really increases the safety. Moving to rapidly growing fires, we have noticed that with fires that are almost instantaneous, the car park quickly fills with smoke, very quickly, much quicker than in linear or alpha t squared growth fires. And we have observed that the traditional fire scenarios that we investigate are rather similar to something like 500, 750 kilowatt rapid growth fires. Rapid growing fires larger than 750 were leading to worse outcomes than the standard design fires that we have used. And with rapidly growing fires, obviously the effect of the height of the car park is there as well. And the higher the car park, the larger the fire can occur there without causing tenability criteria to be breached. To summarize, if we look at the growing fires at evacuation phase, we didn't find any big differences between a linear TNO fire and alpha t squared fires in terms of qualitative assessment. We found that performance at 2.4 meter high car parks is below expected, and at 3.6 is very good. And we also found that jet fan systems, prior to their activation, before the jet fan start, provide generally good tenability conditions in the car park, if the car park has sufficient height. For large fires, we obviously found that the larger the fire, the worse the outcomes. What's interesting is that the difference between 1.4 megawatt and 4 megawatt fires is significantly larger than the difference between 4 and 8 megawatt fires. That's a thing to consider. And we also found that if you have a small car park and a large fire, like 2.4, 2.7 meter high car park, no matter the capacity of the system you put inside, the differences in performance are very, very small. So you cannot compensate the height of the car park with the size of the system, because there is barely any differences in their performance. For rapid growing fires, once again, we don't know what's a good representation of electric vehicle fire. We don't have an electric vehicle design fire yet. From this exercise, we have found that if you have rapidly growing fire and the size of that fire is larger than 750 kilowatts, the outcomes are most likely worse than you would have from currently used design fires for internal combustion engines. And this is something to consider once we receive a design fire for electric vehicles. Finally, last part, the future work, quality of smoke control index. As you have seen, presenting the results of such a vast array of simulations is very difficult, and it's difficult to talk about them and quantitatively assess how the differences are. So we want to automate that process by doing some automated result analysis on the simulations. We're going to define parts of the car park that are under our interest, and we will perform detailed result analysis in them, hopefully combining all of that to a single index that will indicate the performance of the system. And I hope I will be able to share more about this with you soon. Yeah, that's it. I hope you enjoyed that. If you have any questions, please ask them now, or maybe on Twitter. That's probably easiest to find me. I hope you enjoyed that, and yeah, have a great rest of the conference. Thank you very much. Bye.
Okay, so we're live now, so we'll just wait for the viewer count to jump. There it goes.
Oh my God.
Yeah, it's fun to watch it.
Yeah. It's exponential.
Right.
We should model that.
Yeah, I know. That'd be great to have like a data trace of every like transition over here. When you start seeing the world in data sets. So we have about 35 or so. So what we were just kind of talking about based on your talk was the post-processing capabilities. Maybe if you can speak a bit about that before the questions come in here.
It was. I mean, it's when you reach the scale when you have dozens and maybe hundreds of simulations, it's not possible to just do it by normal means. So you either have to employ statistics, as in find the simulations with maximum minimum values and then work them in particular. And because we are talking about transient phenomena, we really like to investigate how things change with time. And naturally, you do that by looking at a video, but that's like really inefficient when you have this many simulations. So these data plots, space-time plots that I've actually saw them at Malaga and FEMTC some years ago, and it was like from that moment, it was like I was amazed by the capabilities these plots can give, and this is why we've tried to use this for investigating the car park here, because it's also like very efficient because it's fairly simple geometry, and we will definitely use more of that in combination with some statistics and some kind of criteria, automated criteria that we can program and have plot showing when that had. Yeah,
that's great. I did see a question come through stage chat here too. Did you model sprinklers?
No, it's not. Just smoke control was already huge enough complexity in here, and Poland is not really a sprinkler country, so we are also kind of locally biased. Probably I would like to do that at some point, but yeah, at this stage we did not consider that.
And then I also had this question, and there's one here from Kristen. Just how did you choose your plot location? Why write that placement, that specific line for the space time?
We did. We did many more plots. It's like we have many plots for this presentation. I chose this location because it's nice, because it shows the plot through the smoke plume, and shows some of the surrounding area at that stage. And it's quite nice because you can at the same time visualize a layered behavior of the smoke, and you can capture the plume temperatures at one go. So you get many things at once. But you would most likely be interested in this kind of visualization next to an evacuation doors or inlets. So yeah, that's probably yeah, it's very arbitrary where you put that. But because we are now have all the data set in data tables, we can plot probably wherever we want. So whenever we notice something interesting, we can immediately jump into investigation in that regime. Yeah.
Another question here about, was the car park exposed to wind or was it underground in this example?
It was enclosed car park with open walls in and neighboring small compartments, so we did not have any wind exposure. No.
Do you have any validation studies with this, with any kind of experiments or cold smoke or anything?
Not something citable, no, I wouldn't claim it as a validation. However, we have performed hot smoke tests in many car parks for which we have done CFD simulations, and usually the flow pattern in the experiment confirmed the predictions of the CFD more or less. So usually more. So we are fairly confident with that. I don't claim these simulations are a true representation of the cause of a fire in a car park, because they obviously are not, but still they are kind of useful to explore how the parameters affect the smoke exhaust. So yeah, we don't really have good validation of that, but we still think that the findings can be interesting and valuable, and maybe also helpful in designing future experiments on the things that we find out the most interesting ones.
There's a question here about fire spread from a cluster of burning cars to perhaps a car target on the opposite lane. Do you think that's an area of concern to include in this analysis?
Yeah, that's an amazing thing. We currently do not do that. What I thought about is more like introducing a tenability criterion for my, acceptance criterion for my simulations if the conditions in the car park promote further spread of the fire or not. Because if you take a look at the car park fires, you either have fires in the real world. You either end up with fires of 1-2 vehicles that are mildly burned, or a single vehicle that's completely burned, and the other group of fires are catastrophic fires of the dozens of vehicles. You don't really have fires of 5 or 6 vehicles. This is because when some sort of critical mass is reached by the fire in the car park, it will eventually snowball out of control, because you don't have any way to access the source of the fire and efficiently extinguish it, unless you have sprinklers, obviously. So we figured out, okay, in this round, we will focus on these rather small fires, but at the same time, we will at some point estimate if this fire could promote conditions that could snowball it out of control. And there is a PhD thesis of Mohammed Tohir from Canterbury, who has done probabilistic fire spread in car parks, and some criteria that he introduced that are the start criteria for fire to jump from vehicle to vehicle. We will use this as acceptance criteria, and we will say that, okay, for this group of simulations, we expect that the fire might have snowball out of control, and for this group is rather unlikely. This is how we want to deal with it. This is why we went into design fire also, not probabilistic.
Right. Interesting. Okay. Here's a question just more on the practical side. Will you also compare installation costs and benefits compared to the cost of just making a higher ceiling in the garage?
Yeah, I mean, the height of the car park is one of the most profound findings of this project, because from my engineering experience, I would not say that it's that important. I would say it is important, but I had no idea it is this important. Yeah, we would love to promote higher car parks in our country, and we are aware that it increases the cost of the land work and so on. So it's a huge cost to increase the height of the car park. And to answer that, we will at some point perform J-value analysis on the efficiency of the solution, whether it's more efficient to increase the height or improve the systems. However, one thing that's important for small car parks, for low height, for 2.4, 2.7, we found that increasing systems does not really improve the outcomes. So that's also huge. You cannot just jump from a tiny car park into more expensive system and hope that it will solve the problem magically.
Right. Let's see, we've got a couple more questions here. So which turbulence model did you use? Just Dan noticed some improvements for dynamics Węgrzyński instead of the default Deardorff viscosity.
I don't remember which version of the FDS was used, and I think it was 6.7, and we used the default at that point. I think it's Dynamics Mag at okay. That. It was not 2015 model. Yeah.
Okay. Yeah, and then one more here, and then I'll just recommend, if you can stay here and maybe answer a few more.
Yeah.
That'd be great. Otherwise, because we'll shut this down. But maybe just looking at what failure criteria has been used here. So visibility of 10 meters, 30 meters, what?
Yeah, at this point, we have used just 10-meter visibility as just the first criterion, because this is preliminary results. So it's just the first analysis with 10-meter visibility. But we are aware that this is not the perfect version. This is why we want to introduce this algorithm to do the full analysis instead of us, in which it will analyze visibility at different levels, at different places of the car park. Maybe we will introduce some sort of ray tracing as well, because now we have the cloud of results in which we can fairly easily implement ray tracing to find out the true visibility, because visibility in smoke is just a fancy way to say smoke mass density, of course. So right. Yeah, we will do that. And we also have used temperature criteria. That is 60 degrees for the human height, or 200 degrees that correlates with 2.5 kilowatt per square meter radiation from the layer for the layer itself, and that's for humans. And we will use Tohir's conditions for the fire spread to investigate the spread of the fire possibility.
Sounds like a lot of really great work to do even more moving forward. So it sounds very interesting.
Really, it was a side project and it kind of grew big. So. But yeah, I'm happy with it. I'll try to answer the other questions in the chat.
Yeah,
so go on.
I appreciate that. Well, thank you very much for the talk and for this great Q&A, and we look forward to your work as you move forward.
Thank you very much, Brian.
Take care.
Thank you.